Welcome to this lecture on Module 3 of the course MEMS. I am Dr. Semi Zarin Sleba, Assistant Professor, Department of Electronics and Communication Engineering, Rajagiri School of Engineering and Technology. The topic of discussion in this module is scaling laws in miniaturization. The objective of this chapter is to provide engineers with a few selected scaling laws that will make them aware of the physical consequences of downscaling machines and devices. So in this lecture, we will be dealing with the scaling in geometry, scaling in rigid body dynamics, and scaling of certain physical parameters like electrostatic and electromagnetic forces, electricity, fluid mechanics, and heat transfer. There are generally two types of scaling laws that are applicable to the design of microsystems. The first type of scaling law is strictly dependent on the size of the physical objects, such as the scaling of geometry. While scaling in geometry, the behavior of objects are governed by the laws of physics. For example, scaling of electrostatic and electromagnetic forces. The second type of scaling law involves the scaling of phenomenological behavior of microsystems. In this category of scaling, both size and the material properties of the system are involved. For example, thermofluids in microsystems. Volume and surface area are two physical quantities that are frequently involved in micro-device design. Volume relates to the mass and weight of the components designed. Mass of a component, in turn, relates to both mechanical and thermal inertia. And this thermal inertia is related to the heat capacity of the solid, which is a measure of how fast we can heat or cool a solid. Such a characteristic is important in the design of a thermally actuated device. On the other hand, surface properties like surface area are related to pressure and buoyant forces in fluid mechanics. It is also related to the heat dissipation or heat absorption by a solid. For example, surface pumping by using piezoelectric means is a practical way of driving fluids flow in capillary conduits. So when a physical quantity is to be miniaturized, the design engineer must take into consideration the magnitudes of the possible consequences from the reduction on both volume and surface area of the device. The surface area to volume ratio of a solid is commonly known as the S by V ratio. Now, let us understand what is the effect of scaling in geometry on the S by V ratio for a solid. For example, we will take a solid of rectangular geometry. So let the linear dimension of the solid be represented by small l. The volume of the solid V will be proportional to L cube, whereas the surface area S will be proportional to L square. So taking the surface area to volume ratio, L square by L cube will give S by V ratio will be proportional to L raised to minus 1. From this, it can be inferred that if we reduce the linear dimension of the solid by 10 times, that is, L is reduced to L by 10, then the volume gets reduced by 1000 times and the surface area gets reduced by 100 times. This figure shows an interesting contrast of two living objects, an elephant and a dragonfly. The elephant has an S by V ratio of 10 raised to minus 4 per millimeter, whereas the dragonfly has S by V ratio of 10 raised to minus 1 per millimeter. These distinct S by V ratios explains why a dragonfly requires little energy and power and thus low consumption of food and water to fly, whereas the elephant has a huge appetite for food in order to generate sufficient energy to make even a slow movement. Since the S by V ratio, that is the surface area to volume ratio, for elephant is much lesser than that of a dragonfly, the elephant can never fly even if the size is miniaturized. Now we will see another example for scaling in geometry. Micromirrors are essential parts of microswitches which are used in fiber optic networks in telecommunication. These mirrors are expected to rotate at a tightly controlled range at high rates. So in this example, we will estimate the reduction of torque required in turning the micromirror when the dimensions of the mirror are reduced by 50%. So as you can see in this figure, B, C and T are the dimensions of the mirror. And here the mirror is placed such that it turns with respect to the YY axis. Now, the torque required to turn the mirror will be proportional to the mass moment of inertia of the mirror about the y-axis. That is, torque is proportional to Iyy. Iyy is the mass moment of inertia about the y-axis. Now, the mass moment of inertia Iyy is given in terms of the dimensions of the mirror as Iyy is equal to 1 by 12 rho into B C cube T. In this example, if we are reducing the dimensions of the mirror B, C and T by 50%, we need to substitute B by half of B, C by half of C and T by half of T in the formula for Iyy. While calculating, we get the new mass moment of inertia I dash Yy. It will be equal to 1 by 32 times the previous Iyy. So this essentially means that the torque required to rotate the mirror is reduced by a factor of 1 by 32. So because of the scaling in the linear dimensions by 50%, the torque required to turn the mirror has reduced by 32 times. Now, in order to design micro actuators and micro sensors, the principles of rigid body dynamics has to be applied. Before the design of an actuator, an engineer has to resolve issues like the required amount of a force to move a part and how fast the desired movements can be achieved, that is the timing, and how readily a moving part can be stopped. All these issues relate to the physical parameter called inertia of the actuating part. And the inertia of a solid is related to its mass and acceleration that is required to initiate or stop the motion of the solid. So when trying to miniaturize these components, one needs to understand the effect of reduction in size on the power, force, pressure, and the time required to deliver the motion. Displacement or the distance moved by a rigid body will be proportional to the linear dimension represented by small l. From the fundamental equation that mass by volume is equal to density, the mass of the body m will be proportional to the volume and which is proportional to the cube of the linear dimension, that is L cube. Mass will be proportional to L cube. Velocity of the body v is displacement by time, that is s by t. So velocity will be proportional to L into t raised to minus 1. Now displacement is given by the formula s is equal to v0t plus half at square, where v0 is the initial velocity, a is the acceleration and t is the time. Now if we consider that the initial velocity v0 equal to 0, then the displacement s becomes half at square, from where we can write the acceleration a is equal to 2s by t square. Now substituting in the formula for force, F is equal to mass into acceleration. Substituting acceleration is equal to 2s by t square. We can convert each of these parameters into their corresponding linear dimensions as mass will be proportional to L cube, S will be proportional to L, and T will be proportional to time. That is, when it is taken to the numerator part, it becomes T raised to minus 2. So, in total, force will be represented as L raised to 4 T raised to minus 2. In 1989, William Trimmer proposed a unique matrix to represent force scaling. It is a matrix which has the generic name of force scaling vector, represented by F is equal to L raised to F. It has 4 elements: L raised to 1, L square, L cube, and L raised to 4. Parameters related to force such as acceleration, time, and power density, which is represented by P by V, are defined using this force scaling vector. We will see how each of these parameters is represented using Trimmer force scaling vector. First of all, we will take acceleration. Acceleration A is equal to force by mass. Now, force can be represented using the force scaling vector L raised to F, and mass is proportional to volume, which is proportional to L cube. So, mass L cube coming to the numerator side, it becomes L raised to minus 3. So, in total, we will get acceleration A is equal to L raised to F into L raised to minus 3. Now, you replace L raised to F by the force scaling vector consisting of the 4 components. Now, this operation L raised to F into L raised to minus 3 is carried out by multiplying each of the elements of L raised to F into L raised to minus 3. So, L raised to 1 into L raised to minus 3 will give the first component L raised to minus 2. Similarly, L square into L raised to minus 3 will give L raised to minus 1, the second component of the acceleration vector. Similarly, L cube into L raised to minus 3 will give L raised to 0, that is the third term, and the fourth term will be L raised to 4 into L raised to minus 3, which will give L raised to 1. So this will be the vector representing acceleration. In a similar way, time also can be represented using Trimmer force scaling vector. We know that force F is equal to m into a. Acceleration can be substituted as 2s by t square. Now, s is the displacement. From here, the time t can be written as root of 2s into m by f. Now, we will replace s as proportional to L raised to 1, where L is the linear dimension. Mass is proportional to L cube. And instead of the force, we can write the force scaling vector L raised to F. Now, L raised to F, when carried out over into the numerator, it becomes L raised to minus F. And since it is the square root of this, the whole will be raised to the power of half. So working this out, we will get the 4-element time vector, which is L raised to 1.5, L raised to 1, L raised to 0.5, and the fourth element being L raised to 0. When we are scaling down or miniaturizing a MEMS or a microsystem, we have to ensure that the power used to drive the device or system is properly scaled down to. And in practice, we use the term power density rather than power. Power density is defined as the power by volume. The power density is an important factor because insufficient power results in inactivity of the system, whereas excess power results in overheating and structural damage of the device. Now, in order to analyze the scaling of geometry or linear dimension on the power density P by V0, the power can be written as force into distance by time. So this is power is replaced as force into distance by time into 1 by V0. Now each of these parameters we will represent using its relation to the linear dimension. So force is related as proportional to L raised to F. S is the distance which is related to the linear dimensions as L raised to 1. And the proportionality of the time we have already found out in the previous slide, which is replaced here. L raised to 1 L cube L raised to minus F whole raised to half. And then again V0, which is the volume, is proportional to L raised to 3. So that also is replaced here. Now working this out, we will get a 4-element vector which represents the power density. So the first element will be L raised to minus 2.5. Second one is L raised to minus 1. Third one is L raised to 0.5. And the final element is L square. So now here we have found out a set of vectors for force scaling, acceleration scaling, time scaling, and power density scaling, which represents scaling of rigid body dynamics. This table is very useful in scaling down devices in a design process. The order number in the table, that is the first column of this table, means the order of reduction in relation to the force scaling vector, which is shown in the second column. Now, on the basis of the force scaling vector, we will estimate the associated changes in acceleration, time, and power supply to actuate a MEMS component if its weight is reduced by a factor of 10. Now, weight of the component W is given by mg, that is, weight is proportional to mass and mass is proportional to the volume, which is related to the linear dimension as L cube. So mass is proportional to L cube. That makes weight also proportional to L cube. So the order 3 scaling from the table for force scaling is chosen. So based on that order 3 scaling, the acceleration A is proportional to L raised to 0. That means that there will be no reduction in the acceleration, or the acceleration will have no change. Whereas time is proportional to L raised to 0.5. That is, there will be L raised to 0.5. Here in this case, L is equal to a factor of 10. So 10 raised to 0.5, there will be 3.16 times reduction in the time to complete the motion. And power density P by V0 is proportional to L raised to 0.5. That is, there will be 10 raised to 0.5, again 3.16 reduction in the power density. There is a 3.16 times reduction in the power density P by V0. So the power consumption P will be equal to 3.16 into V0. V0 is the volume which reduces proportional to L cube, or it will be proportional to the weight. So the weight is reduced by 1 by 10th. So in order to obtain the power consumption after scaling down, P will be obtained as 3.16 into 1 by 10. 1 by 10 is the scaling of the volume. So this will make it the power consumption reduced by 0.316 times. The mathematical expressions for electrostatic forces have been discussed in Module 2 of this course. Here we will revisit the configuration of a parallel plate capacitor in order to discuss the scaling of the electrostatic forces along with the scaling in the dimensions. In the parallel plates shown in this figure, W and L are the width and length of the parallel plates respectively. D is the distance of separation between the plates. The expression for electric potential energy induced in the parallel plates is given by U is equal to half CV square, which is also equal to epsilon 0 epsilon r WL V square by 2D. Epsilon 0 and epsilon r are respectively the permittivity and the relative permittivity of the dielectric medium between the two electrodes, and V is the applied voltage. The voltage V in the expression for electric potential energy is also known as the electric breakdown voltage of a capacitor. This breakdown voltage varies along with the gap between the two parallel plates, that is D. The variation of V along with D is shown in this graph. It can be seen that the breakdown voltage V drops drastically with the increase of the gap for the values of D less than 5 micrometers. As the gap D becomes greater than 10 micrometers, the voltage V increases linearly with D. That is shown in this portion of the graph. We can thus assert that the applied voltage V is proportional to D, or in scaling, we can say that voltage V is proportional to L raised to 1 for the working range of D greater than 10 micrometers. We can thus express the scaling of the electrostatic potential energy U as follows. Epsilon 0 and epsilon r are not proportional to the linear dimension. Therefore, they can be written as proportional to L raised to 0. W, L and D are proportional to L raised to 1. As discussed in the earlier slide, the applied voltage V is proportional to L raised to 1. So taking all these parameters into consideration, the scaling of the potential energy U can be calculated as equal to L raised to 3. So what is the inference from this is that if the linear dimension or the linear size of the electrodes is reduced 10 times, the reduction in the potential energy will be 10 raised to 3 or 1000 times. Now let us consider the electrostatic forces which are produced in the three directions in the parallel plate arrangement. First of all, in the direction of the separation distance D. Fd is given by minus dou U by dou D, which is obtained as equal to minus half into epsilon 0 epsilon r WL V square by D square. Now taking the scaling of each of the parameters in this expression along with the scaling of the linear dimension, epsilon r and epsilon 0 are not proportional to the linear dimension. Therefore, they can be written as proportional to L raised to 0. W, L and D are proportional to L raised to 1. B is proportional to L raised to 1. So, taking all these parameters into consideration, Fd is obtained as proportional to L raised to 2. So the inference from this is that a 10 times reduction in the linear size of the electrodes results in 100 times reduction of the electrostatic force in the direction of D. The expressions for electrostatic forces in the direction of L and W are also given as Fw is equal to minus dou U by dou W, which is obtained as half of epsilon 0 epsilon R L into V square by D, and FL will be equal to minus dou U by dou L, which is also equal to minus half into epsilon 0 epsilon R W V square by D. When calculating the scaling of electrostatic forces Fw and Fl, we also obtained it as both proportional to L square. So the same inference as in the previous case is existing here also. That is, a 10 times reduction in the linear dimension will cause 100 times reduction in the electrostatic force. The principle of electromagnetic forces is well known. That is, when a current carrying conductor is placed in a perpendicular magnetic field, an electromagnetic force is experienced in a direction which is perpendicular to both the magnetic field and the current. Electromagnetic forces are the principal means of actuation in most machines in the macro scale. Now we will examine the scaling of this electromagnetic force when the dimensions of the component are reduced. The EMF induced in a conductor with n number of turns is given by Faraday's law, where EMF E is given as equal to n into d phi by dt. The incremental electromagnetic energy du can be expressed as E into I dt. Now, this can be integrated in order to find the value of the total electromagnetic energy U, which is obtained as half Li square. L is the self-inductance of the coil. The electromagnetic force is obtained by the partial differential of the electromagnetic energy. That is, force is equal to dou U by dou X. It is obtained as equal to half I square into dou L by dou X. Now, the relationship of each of these parameters I, L and X with the linear dimension is examined. So the current I is directly proportional to the cross-sectional area. So cross-sectional area is expressed in linear dimensions as L square. So I will be proportional to L square. So in this expression we have I square. So force should be proportional to L square into L square. Whereas L is proportional to L square, L, and X is also proportional to L. So they cancel each other. So in effect, we get that the electromagnetic force is proportional to L raised to 4. So the scaling of electromagnetic force with the linear dimension, we have obtained the expression as proportional to L raised to 4. So the inference from this is that if we are reducing the wire length by 10 times, that will lead to 10 raised to 4 or 10,000 times reduction of the electromagnetic force. Whereas 10 times reduction in the size of a parallel plate means that 10 square or 100 times reduction in the induced electrostatic forces only will be there. And this is the reason why electromagnetic forces are not commonly used in MEMS and microsystems as the preferred actuation force, because with the reduction in the linear dimension, the reduction in the electromagnetic force produced will be much higher compared to that of the electrostatic force. Electricity is a dominant source of power to MEMS and microsystems. So, scaling of electricity is a very important design issue. Some of the scaling laws related to electricity may be derived from simple laws of physics. The first one, resistance, R is equal to rho into L by A. So each of these parameters are scaled against the linear dimension. L will be proportional to L raised to 1, whereas the area A is proportional to L square. So in total, the resistance will be proportional to L raised to 1, L raised to minus 1. Here, the resistivity rho is dimensionless. It is not proportional to the linear dimension, so it is taken as L raised to 0. The next parameter is power loss P, which is equal to V square by R. Now, V is not related to the linear dimension, so we will take it as L raised to 0, whereas R, which was found earlier, is proportional to L raised to minus 1. So here we get power loss P is proportional to L raised to 1. The next parameter to be analyzed is electric field energy U, which is given by half epsilon E square. E is the electric field strength. Epsilon is not related to the linear dimension, hence it can be expressed as L raised to 0, whereas the electric field strength E is given by the voltage divided by distance. Distance is proportional to L, so electric field strength E will be proportional to L raised to minus 1. So substituting this, electric field energy will be proportional to L raised to minus 2. The power for performing a desired function is expressed as the ratio of the power loss to the available energy EAV. The scaling of this ratio of power loss to the available energy is analyzed here. As discussed in the earlier slide, the power loss P is proportional to L raised to 1, whereas the available energy EAV is proportional to the volume. So it will be proportional to L cube. So in effect, the ratio power loss to the available energy will be proportional to L raised to minus 2. This relationship indicates that a significant disadvantage of scaling down of power supply systems. That means 10 times reduction in the size of the system leads to 100 times greater power loss, because here with the linear dimension shrinking to 1 by 10th, we can see that the ratio of P by available energy EAV will be 1 by 10 raised to minus 2. That is, it will become 100 times greater. So the power loss is very high when the reduction in size occurs. Now we move on to the scaling in fluid mechanics. Consider a fluid flowing through a small circular conduit of length L and radius A, small a. The rate of volumetric flow of the fluid is given by Hagen-Poiseuille's law, which is expressed as Q is equal to pi a raised to 4 delta P by 8 mu into L. Here A is the radius of the circular conduit, delta P is the pressure drop over the length L, and mu is the dynamic viscosity of the fluid. So for a given pressure drop delta P by L, the volumetric flow Q will be proportional to A raised to 4, because in that expression for delta P by L, which is a constant, the volumetric flow Q will be proportional to only one parameter, that is A raised to 4. So converting this into the linear dimension, A is proportional to L, so Q will be proportional to L raised to 4. The volumetric flow Q can also be expressed as equal to the cross-sectional area of the pipe AS into the average velocity of the fluid, V average. The area of cross-section of the pipe is given by pi a square. Now for incompressible fluids, V average is a constant when the radius A is constant. From the expression for the volumetric flow Q, we can write the pressure drop per unit length as equal to delta P by L, which is equal to minus 8 mu into V average by A square. So here mu and V average will be constants since velocity of the fluid will be constant for a constant radius. And so the pressure drop per unit length will be dependent only on A square, and A is proportional to L. So delta P by L will be proportional to L raised to minus 2. The pressure drop for a section of a capillary tube of length L can be obtained by multiplying this with L. That is, delta P will be equal to minus 8 mu V average into L by A square. So the inference is that if the radius of the tube is reduced by 1/10, the volumetric flow is reduced by 1 by 10,000 because volumetric flow Q is proportional to A raised to 4. And the pressure drop per unit length increases by 100 times because pressure drop per unit length is proportional to L raised to minus 2. It is extremely difficult to push fluids through microchannels because of this large pressure drop. Now, if the capillary tubes are having a radius in micrometer range, the pressure drop per unit length will include the capillary effect also. So, delta P by L can be calculated as equal to 2 gamma by A into L. So, this leads to A being proportional to L and L also being proportional to A is the area of cross section, it is proportional to L square, and L is the length of the tube, which is proportional to L. So this will lead to delta P by L being proportional to L raised to minus 3. Gamma is the coefficient of surface tension, which is not dependent on the linear dimension. As discussed just now, it is extremely difficult to push fluids through microchannels because of the large pressure drop. So micrometer and submicrometer scale fluid mechanics do not use conventional volumetric pumping. Some of the alternative pumping techniques that are used are electroosmotic pumping, electrowetting pumping, electrohydrodynamic pumping, and piezoelectric pumping. In piezoelectric pumping, force is generated on the tube wall to drive the fluid flow. It is similar to squeezing of the toothpaste from a plastic tube. So the force will be proportional to the surface area of the tube S, which is equal to 2 pi into A into L. A is the radius and L is the length of the tube. The equivalent volume of the fluid will be V is equal to pi A square into L. So the S by V ratio can be calculated as 2 by A. Since the surface force required to pump the volume of fluid is proportional to the S by V ratio, the force will be proportional to 2 by A. That means A is proportional to the linear dimension L. So force will be proportional to L raised to minus 1. Heat transfer is an essential part of the design of many microsystems. For most cases, heat transmission in microsystems is in the modes of conduction and convection. In some special cases, heat is also transferred by radiation. Here we will take an overview of the scaling of heat transmission using conduction and convection. The scaling laws are available in two regimes, one being in the meso and micro scale, and the other is the submicrometer regime, that is 1 micrometer or lesser dimensions. For one-dimensional heat conduction along the x coordinate, we have the heat flux Qx is equal to minus K into dou T by dou x. So generic form of heat conduction in a solid is given as capital Q is equal to the heat flux small q into the area A. Substituting the value of heat flux as equal to minus K into delta T by delta X, we get heat conduction Q is equal to minus K into delta T by delta X into capital A. Now converting each of these parameters into their equivalent linear dimensions, K is not linearly proportional to the linear dimension, neither is delta T, but area A is proportional to L square and delta X is proportional to L raised to 1. So this sums up to the heat conduction Q being proportional to L raised to 1. So this was the case of meso microscale devices where K had no scaling dimension, that is K was proportional to L raised to 0. But in submicrometer scale, the value of K is equal to 1 by 3 CV lambda. C is the specific heat, V is the molecular velocity, and lambda is the average mean free path of electron. Another factor to be analyzed in scaling is how fast heat can be conducted in solids. That is the time required to conduct the heat. The Fourier number F0 is used to determine the time increments in heat conduction analysis, which is given as F0 is equal to alpha T by L square, which is the rate of heat transfer by conduction divided by rate of energy stored. F0 is the Fourier number, alpha is the thermal diffusivity of the material, and T is the time for heat to flow across the length L. From this formula for F0, we can deduct the formula for the time T, which will be equal to F0 into L square by alpha. Here F0 and alpha do not scale with the linear dimension. The only factor that scales with the linear dimension is L. So T will be proportional to L square. The inference from this is that 10 times reduction in the dimension of the solid leads to 100 times reduction in time to heat the solid. Now let us examine the scaling in heat transfer by the convection mode. Usually, the heat transfer in fluids is in the convection mode. The heat flow between 2 points, capital Q, is given by small q into A, where small q is the heat flux and A is the cross-sectional area, which is also equal to H into A into delta T. H is the heat transfer coefficient, which does not scale along with the linear dimension, but area A scales with the linear dimension as proportional to L square. So here we can say that the heat transfer Q will be proportional to L square. So in this module, we have discussed the scaling in geometry, scaling of rigid body dynamics, and the scaling of some parameters like electrostatic and electromagnetic forces, electricity, and heat transfer with the scaling in the linear dimension. With this, I conclude. Thank you.